So I'm just going to go over a few questions in our problem set A on binomial expansions and view a few different ways of actually being able to expand a binomial. Binomial meaning there's two terms, and if it's a binomial power, it's two terms to the power of n, some number. So you can imagine if it was a number like this, x plus 1 to the power of 3, you might start by just expanding it as if you normally would. Many of us have used the FOIL method before, so this is nothing that new. So here you would simply multiply, maybe you'd go and do the FOIL method at first, and you would come up with x squared plus 2x plus 1, and then maybe you would deal with the second bracket after that, and then you can use the same kind of FOIL or rainbow type expression that maybe you would be used to seeing in textbooks, and this is pretty much the way that you learn to do it in even as early as grade 8. As you go through here, you get x squared, and you have x squared plus, x cubed plus x squared. Move on to the next term, you get plus 2x squared plus 2x plus x plus 1. And from there you'd want to group like terms. And here we come up with x cubed plus 3x squared plus 3x plus 1. However, looking at it, doing it this way is a bit more time consuming. You can imagine if it was x plus 1 to the power of 17, that would take you a really long time. And as we talked about in class, there's a method to do this using Pascal's triangle. Now it's important that you know how to do Pascal's triangle before you actually start using it. So Pascal's triangle at the very top starts with a 1, and that is the same answer you get as your coefficient if you did x plus y to the power of 0. So you start with a 1. Then you have two 1s. And then you get a 1, a 2, and a 1. 1, a 3, 3, 1. And maybe some of you guys are seeing the pattern that's emerging here. And I'll show you that pattern right here in a second. So the pattern here is that if you take the, for example, if you want to get to 2, that 2 emerges from the fact that you took a 1 plus 1 to get to 2. Take a look at the 3 below it. That came as a result of 1 plus 2 equals 3, and the 3 right beside it is the same phenomena that's happening. So you can see as you go down how the numbers get formed, and that is a simple way of making Pascal's triangle. You'll notice that even the numbers along the side, like a 1 right here, is the result of 1 plus what's out on the side, which is nothing. The result of 1 plus nothing is 1. So that's how you would create Pascal's triangle. So important if you're going to use Pascal's triangle that you actually know how to form it, because chances are your teacher won't be giving you that. But it'd be a good tool to keep around and be able to form at any given time. And as we talked about in class, Pascal's triangle gives you the coefficients on the expansion. So if you wanted to take a look at Pascal's triangle for, maybe you have n to the power of, so as it walks down it's n to the power of 1, n to the power of 2, but maybe your n is to the power of 5. So maybe you're looking at a scenario where it is x plus 2 to the power of 5. Now what you can use this is, you can use that entire row, the 1, 5, 10, 10, 5, 1, to give you your coefficients. Now part of the problem in this one is that we have an x and a 2. We're used to seeing an a and a b to the power of n, but that's okay, we're allowed to use an x and a 2. So what we want to do is, starting by just saying, let's let a equal x, and let's let b equal 2. Now instead we have a plus b to the power of 5, and we're fairly familiar with this expansion because it's in Pascal's triangle. So as a result you get this as your answer. Now this is not your answer because you haven't actually put the original numbers back in, so we're going to do that. And when we put in the numbers we get this as a result. From here it's a matter of simplifying. And summarizing, you would get 6 terms, which is 1 more than what n is. Try it on your own, see if you get the same result.